Hello everyone. En français ou en anglais? Bah là, en français. Donc, c'est mon plaisir d'introduire Dominique Aubert, qui est le présent, en franglais, alors le speaker d'aujourd'hui. Il va nous parler de l'évolution cosmique de la réionisation. Dominique était mon premier étudiant en thèse à Strasbourg. Il a travaillé à l'époque sur l'évolution séculaire des systèmes ouverts. Donc, c'est un travail partiellement analytique et partiellement numérique. Il a visiblement pris plus goût à l'aspect numérique puisqu'il s'est ensuite plongé dans les simulations cosmologiques lors de son postdoc au CEA, sous la direction de Romain Tessier, où il a produit la première simulation cosmologique hydrodynamique Mare Nostrum. Et il est devenu, dans la foulée, au bout d'un an, maître de conf, puis professeur à Strasbourg un peu plus tard. Il s'est investi énormément dans le développement de codes de transfert radiatif, en particulier sur GPU. Et il a de ce fait accès maintenant aux plus grands centres de calcul aux États-Unis pour utiliser ces ressources pour faire des simulations de transfert de rayonnement dont il va vous parler aujourd'hui. Il est impliqué dans le développement du successeur de Ramsès qui s'appelle Diablo, qui doit fonctionner sur des nouvelles architectures à base de GPU. Il a encadré 5 thésards dont il va présenter entre autres le travail aujourd'hui. Et il a été brièvement le seul cosmologiste à Strasbourg et il a réussi à accréter un paquet de gens depuis. Donc, Dominique, je te laisse la parole.
Okay. So I'll switch to English. So thanks a lot for the invitation. So it's a great pleasure for me to be here today. It was really close because my train had a lot of issues this morning, but I'm here, and I'm here to talk about the time evolution of cosmic reionization. So most of my work is focused on the utilization of models and simulation as written here. And what I'm going to present here, most of the thing I'm about to present here is not actually my direct work, but it's the work that has been done by my collaborators, and especially my PhD students. So Émilie Telly and Julien Higel for the most part. And I also have other things that I will present that were made by my previous PhD students. So I'm mostly here to showcase the work made by other people. So we're going to talk about cosmic reionization, and so it's difficult now to discuss about this specific era in the history of the universe without mentioning the James Webb Space Telescope. So 20 months ago, this picture was the first publicly released image of this telescope by President Biden himself. And this kind of picture, and many of them later on, gave us for the first time an unprecedented view of a distant era, both in space and for us, the most interesting part in time, and gave us access to galaxies that were living in the first billion years of the universe. So this is the kind of data that this instrument provided us. And for example, those were the kind of results that were very quickly obtained. So for example, here provided by a work led by Hakim. In fact, this work has been published in 2023, but those plots are getting updated basically on a day-to-day basis. And now we have, like, I was about to say an easy, but it's becoming mainstream, the fact that we have access to galaxies with redshifts in the double-digit regime, right? It's normal now. It's the new normal, and now we have access to these galaxies in this very early time in the history of the universe. So here, for example, those are examples of galaxies with redshifts beyond 10. And at this stage, you are deep inside the first billion years of the universe, which is what we call the epoch of reionization, and that's going to be the main focus of my discussion today. So just to give you a more dynamic idea of what's going on at this time and what I'm mostly interested in, here, this is a model that I did a while ago, so more than almost 15 years ago. And this is a simulations that show you the time evolution of the distribution of neutral fraction in a cosmological box. Okay, so the red regions are ionized and hot regions. The blue colors show you the regions where the gas, and when I'm talking about gas here, I'm talking about hydrogen, where the gas is still cold and neutral. And what you see is this pattern, evolving pattern, typical of the epoch of reionization, where you have bubbles created by the radiation produced by the first galaxies and the first stars. And you have ionized bubbles that grow, that multiply, and that eventually percolate 1 billion years after the Big Bang, leading to the end of reionization. So this transition is mostly powered by stars and galaxies, okay, with some contribution of active galactic nuclei. And again, this pattern this network of bubble, this network of H2 region is also very interesting because it traces the large-scale distribution of structures, of the first structures that appear in the universe. So that's the thing I'm interested in, is trying to understand how this time evolution can be studied and constrained in order to go back to the properties, to the sources that produced this scenario. So just to give you a little bit more of context, this is a timeline of the history of the reionization produced from one of the simulations that we did in Strasbourg. And just to give you an idea of the time scales and range of redshift that we are interested in. So here, the time duration that is being covered by the x-axis here is around 1 billion years, okay? 1 billion years, that's the canonical value that we give to provide a rapid number to say when the reionization was finished, was completed. That's where we are here. It corresponds to a redshift around 5.6, okay? Even though this is an ongoing discussion, and this is something I'm going to present just later on. And here in this timeline, what you see is the distribution, the time evolution of the distribution of neutral gas as a function of time, okay? Dark regions, such as this one, shows you where the gas is ionized. The hydrogen is ionized. And as you can see at early time, after the production of the cosmic microwave background, by definition, the cosmic microwave background was produced, hydrogen was neutral at that time. Okay, so we are a few 100,000 years after the Big Bang. Then the epoch that follows is called the dark ages. So you have gas, structures that are growing just under the influence of gravity. And, but you don't have astrophysical sources yet. Okay, you don't have the condition to trigger star formation, to trigger galaxy formation, and essentially it's just gas collapsing and organizing itself in the let's say the early stages of large-scale structure formation. Then you have what we call the cosmic dawn. The cosmic dawn is the epoch where the first astrophysical sources appear. We don't know exactly when it took place yet, okay, but models indicate that it should take place around the redshift of 3020, something like this. Okay, so that's very early in the history of the universe, and it corresponds to a universe that has around 150 to 100 million years. Okay, so that's very early in the history of the universe. Okay, then the first source appears. Here they are spotted as red dots. Okay, so those are galaxies. But I didn't tell you that the Y scale here is about 120 megaparsecs. Okay, so just to give you an idea of the range of distances that is shown here. The first galaxies appear, they create radiation, ultraviolet radiation that ionize the gas around them. There are more and more galaxies as time goes by. The bubbles are larger and larger because you always pump radiation into the gas, and you end up with a universe that is fully reionized by a redshift of 6, basically 6.5, 1 billion years after the Big Bang. Okay. So those are the times and the redshifts that we're going to deal with today. So here there are a few things that I added as bullet points, but they're just a summary of what I just said. So here we're talking about the reionization of hydrogen. Okay, so for example, helium will also be reionized, but much later on, and that's not the topic that I'm going to discuss today. Okay, we believe that the dominant source of radiation, the astrophysical source that dominate the budget of ionizing photon are galaxies, stars in galaxies, even though there's some contribution from active galactic nuclei. Okay, and yeah, the image that we have in our head, okay, is creating ionization fronts around sources. Ionization fronts propagate and eventually percolate. Okay, and at the end of the day, you end up also with an IgM which is hot. Okay, it used to be cold and now it's hot, around 10,000, 20,000 degrees. Okay, and once the universe is fully reionized, it's completely optically thin to this kind of radiation, not absolutely, completely. This is something we're going to discuss, but mostly. And you have a UV background that is basically everywhere at this time, created by the source. Okay, so here also are a few points about the cosmic dawn. This is the time where the first stars are created, okay? And as I said, we don't know exactly when. And it's also the time where the intergalactic medium is being heated by the first X-ray sources, X-ray binaries, for example. And this is something that is important for the observation in the radio range of this process. Okay. So those are a few key points of about the timeline of reionization. And here I'm going to go briefly trying to do an overview of what is the observational status in the past, but mostly what's going to be the future of the observations of reionization. So here, what you have on this plot are historical plots. Okay, on the left-hand side, here you have a collection of Lyman alpha forest. So those are spectra along the sign of quasar. This is a very classic paper by Fan et al. In 2006, where they're showing the spectra of quasars at the redshift going from 5.7 to 6.4. Okay. And the thing that we see as we go deeper and deeper in terms of redshift is that we see that the signal in transmission gets weaker and weaker until basically you don't have any transmission anymore in where you should in principle see the Lyman alpha forest in the spectra of quasar. Okay, so for example, here at very high redshift, you can see it's almost completely flatlining. And it indicates us that those quasar, and more precisely, the gas along the line of sight of this quasar is still very neutral. Okay, it's still very neutral. It gets very heavily absorbed, and therefore those quasars here are in era that are before the reionization, when during a time where the gas was still neutral. And as you go down in redshift, you start to see transmission appearing again. That's because you have windows where the gas is ionized, where absorption is not as strong as it used to be, and that's in a regime where the universe is in post-ionization. Okay, so the idea here is that when you study, for example, the Lyman alpha opacity using the spectra, it can give you a timing of when the reionization took place. Okay, and here the transition takes place around the redshift of 6. That's how it was used to do before. Planck cosmic microwave background experiments are also able to put constraint on when the reionization took place. Just because the photons from the cosmic microwave background, they scatter on electrons that are released during the reionization. And there are ways to estimate the amount of scattering, which depends on when those electrons were released. And here, for example, you have several estimates from several experiments, but mostly by Planck here, of the optical depth to reionization, which is the tau parameter. The tau parameter is somehow a measure of the integrated number of scattering of photons, CMB photons, on electrons. So it's an integrated measure. And the latest constraint by Planck tell us that this opacity has a value of 0.58. Okay, that's the number. But it translates into a redshift of reionization, of mid-reionization of around 7.7. Okay. So those two things are consistent because this measure mostly the end of reionization and this measure where the mid-reionization took place. This is how people used to do it in a classical way. Now, the thing is, as I said, it's not completely clear when the reionization ended and when it took place in general. So for example, those are recent results where you have here, for example, a paper by Baker and collaborator, when they give you as a function of redshift, the evolution of the mean free path, okay, of photons, as a function of redshift. And this is done by studying quasars of spectra, spectra of quasars. That's the opposite, okay, sorry. And what you see is that there is a very strong evolution of the mean free path when you go between redshift 5 and 6, okay. So here, this paper translates the same kind of measurements in another space. So here, for example, you have the measure of the Thomson optical depth from the cosmic microwave background. Here, for example, the shaded area tells you are the constraint by Planck. And this line, for example, you shouldn't focus on this one. This line, for example, tells you how this kind of measure translates into the estimate of the optical depth, and you see that it's consistent. And here on the upper left side, you have the time evolution of the ionized fraction. Okay, so the redshift goes from, the time goes from here to here, and the ionized fraction goes from essentially 0 to 1, and the universe is fully ionized around a redshift below, below a redshift of 6. My point here with this slide is to tell you that actually all these modern, so to say, measurements tends to tell us that the redshift probably, the reionization probably ended at a redshift below 6, between 5 and 6, whereas what we used to find in textbooks is that by redshift of 6 is complete. And now it seems that there's more and more evidence telling us that actually the reionization probably took place at a later time, below redshift of 6, 5.5, maybe even 5.2. So this is an ongoing discussion. It's not completely trivial. It's not completely anecdotal, so to say, because a delay like this in redshift amounts to basically 300 million years in terms of time. And 300 million years in a universe which is only 1 billion year old, that's not nothing. And if you compare that, for example, for a typical lifetime of massive stars, that's a lot of time. So when it took place can have an influence on how you interpret this timing. Not only it's not sure when the reionization took place, but actually it's very likely also that it was still very patchy at very late time, which means that from place to places, the reionization was not completely complete, whereas in other places, the reionization was really advanced. This is something that is shown, for example, in this kind of studies, okay, where you have here, again, a spectra of quasars at similar redshift, where some of them, for example, have transmission, telling you that the gas is significantly ionized. And some of them are completely, you see, flatlining like this, okay, which tells you that on the line of sight here, the gas is very opaque. And this is summarized in this plot that gives you as a function of redshift the optical depth here. And something that people realized, let's say in the last decade, is that there is a huge scatter, in fact, of optical depth, even below a redshift of 6, which tells you that not only the reionization likely took place at a later time that we thought, but also it's very diverse in terms of line of sight, environment, and positions. And this is something that I'm really interested in. Okay. So that was the past. That's not the past as still today, but the future also is going to be related to this kind, the future of the study of reionization is going to be related to what I'm going to discuss here. Here you have models that shows you radio emission of the gas. Because the thing is, during the reionization, you end up having this kind of distribution of ionized gas, bubbles, the red bubbles, centered around the sources and the large-scale structures, surrounding neutral regions that are still in blue here. And the thing is, this gas, this hydrogen, when it's still neutral, it's able to produce a radio signal, especially at 21 centimeter. And one of the great goals of many people in the next decade is to be able to try to see this signal of this gas in order to see literally the network of bubble growing, percolating, and seeing the reionization, let's say, in real time, just by looking at the radio signal. Here in the middle panel, you have a simulation of what should be this radio signal, the pure radio signal produced by the neutral gas. And you can see that when the gas is ionized, it's not able to produce radio because the radio signal is produced by the flip of the hyperfine level of the electron. So as soon as you don't have electrons anymore attached to atoms, the gas is not able to produce radio. Whereas the gas that is still neutral is able to produce radio signal. And that's what people want to see. That's what people want to image, really. That's what they want to do. Here on the right-hand side, you have what you should see through an instrument like SKA, okay? For example, accounting for noise, duration of the campaign, sampling of Fourier space, that kind of thing. And you see that an instrument like SKA, even though, of course, you don't have the same level of details of the pure signal, should be, in principle, able to map the distribution of neutral gas during the reionization using the radio signal. It turns out that if you take the mathematical expression of the radio signal, okay, it depends on many, many physical parameters. It has a lot of physical content. It depends on the distribution of gas. It depends on the state, the ionized state of the gas. It depends on the temperature of the gas. It also depends on cosmology, which means that there is a lot of things that are encoded in this radio signal. Okay, so to some extent, for example, if you take JWST, JWST is giving you access to the objects that are producing the reionization, whereas the radio signal should give you access to the material that is getting reionized. So you have a complementary point of view, something to say. So yeah, I'm spending a long time on that, but I think it's important. the thing is that people are already trying to see this radio signal. Here you have example of experiments, okay, trying to do this. So as you can see, this is in the radio range, okay, and fairly redshifted. Just so you know, the signal we're looking for is a 21 centimeter signal, 1420 megahertz. But of course, it's redshifted, and at very high redshift, beyond 10, which means that you end up going at very low frequency radio, very radio signal. So those are experiments that are currently trying to put constraint on the signal produced by the ionized gas during reionization. You have here Nénuphar, here in France, at very low range, which looks, therefore, at the most redshifted signal at the reionization at very early time, in fact, the cosmic dawn. And here you have LOFAR and ERA, who are looking at higher frequency, trying to probe, essentially, reionization at a redshift around 8 or 9, 10, trying to look at that. Okay. So you should know that it's very challenging to do that. I'm not an observer, okay? I'm doing modelization, but I'm completely amazed by the challenge that those people face trying to find a way to do these images. So here, this is a slide that I took from Mertens that gives you basically what is the pipeline of what's going on from the signal that go through the ionosphere that is kept by the antenna that is being processed until you end up with a power spectra of the fluctuations of the radio signals on the sky. But what I wanted to show here are those plots here mostly, okay? So of course there are foregrounds, okay? So for example, there are extragalactic radio sources, okay? They are quite strong. You have diffuse galactic emission, and what you want to have access to is something which is in background of that, okay? And you need, you know, to remove those foregrounds. So, and that's the 21, the cosmological 21 centimeter signal. What I want to put a focus on is the scale here. So the intensity is expressed in terms of brightness temperature. Here you see that extragalactic sources, if you look at the numbers, it's in the 100 range, okay? If you look at the galactic emission, it's in the 10 range, okay? And if you're looking at the cosmological signal, we are in the 10 to the -2 range, essentially. So people here are looking at something which is at the 10 to the 4, 10 to the 5 level compared to the foregrounds, okay? So that's what I would like those people be able to find behind those kind of things. So just, there are constraints, that being said, and there are mostly constraints on the power spectrum, not on images. Instruments are not able yet to produce images, but there are constraints on the power spectrum of the radio signal. And for the moment, there are only upper limits. So this is a compilation of those upper limits of the power spectrum. So here you have the spatial frequencies, okay? And here you have the power spectrum. And those blue bands, okay, is the level of amplitude that is being predicted by models. Okay, so this is the goal, so to say. What kind of sensitivity should you be able to achieve in order to see the cosmological signal of reionization? It's around here, okay? And those are the limits that are currently reached, and the latest one being the yellow line here obtained by the HERA collaboration. And there are still orders of magnitude, okay, going there. But it turns out also that those experiments have a lot of data, and it turns out it's so, let's say, intensive in terms of processing that there are still a lot of things to do, okay, and those limits are expected to move down, okay, with time. That being said, okay, so for the moment, we haven't reached yet the signal expected from the models. That being said, a large class of models are already being excluded, for example, even by the experiment. For example, if the gas in the early universe is very cold, which means that it hasn't been heated. And for example, one heating process that we expect is heating by X-rays created by the first X-ray binaries and X-ray sources. Okay, so if you don't have this source of heating, the gas will be very cold, and it turns out that a very cold gas should produce a very strong signal. Okay, and the fact that we don't see it, for example, for the moment, put constraints on the amount of heating produced at these early times. And for example, a large class of models with very weak X-ray heating are already being excluded, which means that even though we don't detect anything yet, okay, we are already excluding astrophysical models, and that's really a great achievement. Okay, and what we are waiting for is for SKA. Okay, SKA will be a major upgrade compared to this experiment. So, for example, the survey speed will be much larger. Okay, the sensitivity will be also larger as well as the resolution, and So as you might not know, is that SKA is actually split in two instruments. Okay, there's an instrument at low frequency and an instrument at mid frequency, so to say. And the one we're interested in for cosmic ionization is an instrument at low frequency, which is shown here. So this is an artist view. Okay, but the antennas are currently being built. Okay, just so you know, the one we're interested in is what we call SKA-low. Okay, which is in Australia, far away from any source of radio interference. That's the point. And it should be completed by 2028. And it's a network you see of more than 100,000 antenna. And SKA, and this is, for example, the simulation that I showed you previously, should be able to map the gas, really to produce image. And provided that we're able to remove foregrounds and to be good enough, for example, to understand and calibrate the instruments, it should be able to map the gas being reionized during the reionization. Okay, so this is what people are waiting for. The thing is that it's super challenging. It's super challenging in terms of data processing, as I said, for ground removals, understanding instruments, etc. But just being able to digest the amount of data produced by this kind of instrument is a challenge by itself. Okay, so there are many things in terms of big data and massive data processing that will be, for example, many challenges in this field that will be assessed by this instrument. Okay, so SKA should be able to map the thing. And not only that, but you see, the thing is that you're looking at a signal at a given frequency. Okay, 21 centimeter, 1420 megahertz. So by changing the frequency, essentially, you will look at the same signal, but at different redshift, which means that you will have access to literally a timeline of the process just by scanning the frequencies in the frequency range of the instrument. So we should have access to, you see, those kind of light cones, okay? For example, here where you have the 21 centimeter brightness temperature as a function of redshift, okay? And related, of course, to the time evolution of ionized gas, baryon density, source distribution, and so on. So that's really the great thing, that not only you will see the cheese pattern of ionization at a given time, but you will see it at different times. The last one is you see that's the brightness temperature minus the average brightness temperature, because it turns out that in this instrument you don't know what is the absolute value, in fact, of the signal. You only measure a contrast, and this is closer to what you would get from the instrument than the actual signal. Okay. So now, okay, so I spent a lot of time talking about the things that I don't do. Okay, and now I'm going to talk about the things that I do. Okay, so in this context, I'm mostly interested in doing cosmological simulation of the reionization epoch using a full hydro simulation coupled with radiative transfer in order to produce this kind of data. So here you see on the left-hand side, you have a picture that shows you a timeline, actually. Time goes from left to right. Blue regions shows you ionized region. This is a simulation that has been produced by Pierre Osvirk. It's called the CODA2 simulation. It's part of a suite of very massive simulation that he did during the last decade. So here there are a few numbers if you are interested in. So this is a volume covering 90 megaparsec distances, 4096 cube, a lot of GPUs and CPUs, massive calculation in order to try to model the cosmological reionization using fully coupled radiative hydrodynamic simulations. On the right-hand side, it's another simulation made with another code, okay, that I wrote, which is also part of the same suite. But my point is that this is what we do in Strasbourg. In Strasbourg, we've been writing a cosmological simulation code in order to model the reionization. And of course, the end goal is to provide constraints and to what we're going to observe with instruments such as SKA, and also to test if we are just able to understand what's going on during this epoch. Here is the website of the CODA simulation collaboration. Okay, this is a collaboration again, as I led by Pierre Osvirk. And it turns out that there are many results that were obtained with this set of data. Okay, I'm not going to go through all of them because I will focus on a very specific aspect of this work. But you should know that essentially that's the largest cosmological simulation of reionization ever made. In fact, there's another one that has been produced since, CODA3. Okay, but yeah, this suite of simulation is a set of massive calculation dedicated to the study of reionization. So just to give you further details about doing this kind of simulations, It turns out that simulating the cosmic dawn and the epoch of reionization is quite challenging. I mean, doing cosmological simulations is super challenging, but during the reionization comes with its own set of challenges. There are several, or two of them that I want to put a focus on. The first one is that we have a severe scale coupling. Okay. Again, so here, for example, this is a zoom inside one of the simulations that we did a few years ago. So the simulation by itself covers distances of 90 megaparsecs moving, but you should be able, of course, to resolve as much as you can galaxies, because reionization is a process that is driven by radiation produced by stars, by galaxies, and therefore you should, as much as possible, have a detailed description of what's going on into these objects in order to produce accurately the way light is being produced. Okay. That being said, and this is something that was maybe more obvious from a previous plot here, okay, you see the typical scales of the bubbles here. Okay, so this is a model of reionization. That's 300 megaparsecs. The typical size of extended ionized region can be around 50, if not hundreds of megaparsecs. Okay, and it can be shown that in fact, the typical volume that you should at least study if you want to achieve convergence in order to have a good representation of this ionization field is a few hundred megaparsecs, which means that you are a little bit stuck in a situation where you can't do simulation as small as you can in order to gain resolution. Okay, you need to be significantly large. And for example, the CODA simulation, okay, the one that I showed you, they cover distances of slightly less than 100 megaparsecs. They slightly, it's at the limit. Actually, it's probably too small in order to have a good representation, at least of the largest bubbles. So it means that you need to do large simulations with a good enough resolution. And that's a first challenge. The second thing is that, we are doing radiative transfer. We need to know how light propagates into the universe, how it interacts with matter. And we have to do radiative transfer. And the problem is that light propagates very quickly. The signal goes very quickly through the boxes, which means that if you want to simulate a given duration of the evolution of the universe, it takes many, many iterations. Okay, so it's very numerically intensive. Okay, so and in general, even if you put that aside, there are thermochemical processes where you must compute interactions of radiation with matter, which are also very numerically intensive, which means that from the point of view of pure computing, it's quite demanding as a calculation doing reionization simulation. So that's why we spent a lot of time in Strasbourg during the last 2 decades now, at least 1 decade, to use these kind of devices in order to accelerate calculations. So those are GPUs, graphics processing units. And this is what we did in Strasbourg, is that we ported some part of the physics, so radiative transfer, thermochemistry, depending on the codes, even hydro and gravitation calculations, okay, on these devices in order to accelerate the process, okay, in order to make the production of the simulation viable. So we ended up, for example, for radiative transfer, with speed-ups of a few tens compared to a typical CPU calculation. And for example, the movie that I showed you previously, produced in 2010, is one of the very first simulations that we did on clusters of GPUs, okay, in 2010, so almost 15 years ago. Okay, and we produced several codes. Okay, one of them is QDayton. QDayton is a radiative transfer code only. Okay, that can be coupled with a Ramses code, for example, but the GPU part only performs radiative transfer. Okay, QDayton. And I also wrote a code which is called EMMA, which is full cosmological simulation code, where a significant part, well, all the physics are run on GPUs. Okay, somehow it's some kind of a GPU version of a cosmological code that looks very similar to Ramses. Okay, in other words. So this is something that was written later on. So what are the kind of things? Yes. On EMMA, yes. Oh, sorry. Not much, in fact. No. The only thing that are still done on the CPU is dealing with the AMR tree. Okay, so you have in a code like Ramses, you have adaptive mesh refinement. There is a full logistics of going through the tree, going to cells, going to neighbors, and those kind of things are still made on the CPU. Once you have done your logistics, okay, essentially all the data is sent on the GPU, and the calculations after that are made on the GPU. But the logistics of the AMR is still made on CPU. That being said, that's still a major bottleneck, in fact, of the code, okay, because not everything is done on the CPU. On the GPU, sorry. but that's the thing. So here I'm going to go very briefly through a few results that were obtained using this code. So for example, the QDaton code has been widely used in Cambridge by the team of Martin and Elt. And for example, something that they did is that they run many, many models of reionization, okay, using GPU acceleration, trying to reproduce what is shown here, the distribution of Lyman alpha forest opacities. And remember, a few slides ago, I told you that something that people didn't really understand a few years ago is that why was there so much diversity in the distribution of Lyman alpha forest opacities at the epoch of reionization? Why certain regions were completely neutral and opaque and why certain regions were not? Okay. And what they found and what they claim, and I think it's making it's passed through the community, is the fact that reionization probably took place later than we anticipated, okay? Which means that even at a redshift of 6, for example, which is quite early, okay, reionization is not complete yet, in fact. And if you push down the reionization at later times, you'll end up with large fluctuations at very late time, which can be seen in the distribution of, as a function of redshift of the Lyman alpha opacity. And those simulations were able to reproduce that, provided that the reionization took place not at a redshift of 6, but a redshift of 5.5, 5.2, and even lower. Okay, that's the kind of thing. The kind of thing that I did, for example, using this simulation, is trying to look at the local history of reionization. Because you see, very often when we describe reionization, people, they think of it as a global phase transition, so to say, in the history of universe. The reionization took place at this time, redshift 6, redshift 5.5, whatever, okay. But the thing is, reionization is actually a very local process. Depending on where you are, depending on your proximity to nearby sources, depending on the local distribution of absorbing gas, you might experience reionization at very, very different times. Here on the right-hand side, you have a map where the color tells you what is the instant of reionization at each position, when this pixel was reionized. Here you have the value from a redshift of 6 up to a redshift of 15. And something that you can see is that it's not homogeneous. And not only it's not homogeneous, but the range of values can be quite large, which means that depending on your place, you experience reionization at different times. Here, for example, you have dots in these models. Those dots are progenitors of analog of the Milky Way and the Andromeda galaxy. Okay, so for example, looking at the patches here of reionization times, we can see when, for example, a galaxy like the Milky Way experienced the reionization, or when the Andromeda galaxy experienced the reionization. And in fact, we did that for many galaxies in our CODA simulations. Here on the x-axis, you have the mass, the current mass of a galaxy in our model of a halo, z equals 0 mass. And here on the y-axis, here expressed in cosmic time and here expressed in redshift, you have the distribution of when a galaxy today experienced the reionization. And let's focus only on the red line. The thing that you see is that the heavier a galaxy today, the earlier it experienced reionization. And when I'm saying earlier, I'm talking about redshift of 15, 16, and very far away from the average reionization time in this model, which is around a redshift of 7. Okay, so it means that galaxies, just because they are, it's obvious, okay, they are in places where it's overdense, where it's easier to create stars at very early time in galaxies. Therefore, massive objects are expected to experience reionization at early time. And this is what we see. And it's only when you go to the lower low mass end of galaxies that you see galaxies experiencing reionization like the average value, okay? But on a final note about this discussion, not only you have a time dependence, okay, but you have a large scatter as well, which means that you take two galaxies today with the same mass, they can have, some of them can experience reionization at some time, and another one can have experienced reionization a few 100 million years later. Okay, so that's the study of the local reionization made with this model, and it's not without consequences. For example, something that is shown on the plot on the left, and this is a study that has been made by my colleague, Pierre Oswierk, in the CODA simulation, is that it looked at the star formation history, okay, of small galaxies. You see, those kind of halo mass. So this is the star formation history as a function of time, okay? And what you can see is that the star formation history increases, and at some point it drops, just because as light goes in, okay, it suppresses star formation, okay, as reionization takes place, star formation is suppressed inside those small objects because they can't shield from the external radiation. Okay. But what's going on is that this suppression takes place at different times, depending on where those galaxies are. Okay. So here, the different curves gives you the overdensity, the local overdensity, which is a measure of the local reionization time. And therefore, you have objects at different, you have you have objects of the same class that experience reionization at different times, and therefore, which experience a different suppression of their star formation history. Okay. And one consequence of that, for example, here is on the right-hand side. This is another work made by the CODA collaboration, where here, for example, you have the time evolution of the luminosity functions of galaxies inside the simulation. Okay. This is taken in a region that has been reionized between a redshift of 7 and 9. And what you see is that as a function of time, okay, the luminosity function in this region, of course, it changes, but more importantly, it flattens. Okay, you see it flattens just because you suppress a star formation in a given range of luminosity, a given range of halo mass. And depending on when you experience reionization, this flattening of the luminosity function will take place at different typical luminosities and therefore at different typical mass scale. So you see the fact that reionization is not an homogeneous process, but in fact a very local process, is something to be taken into account for galaxy formation in general. Okay. So now I have like what, 15 minutes, something like this, or good or not? Yeah, 15 minutes. Okay. So in the last 15 minutes, I'm going to discuss about what I've been doing very recently. It will be very fast, it will be very brief because I don't have much time. But something I've been very much interested in is, okay, so here we have a process where you have bubbles that appear, that grow and percolate. The question that I really had in mind is how do I characterize that? How do I characterize this process of percolation, of evolution? Okay. And this is something that goes way back. With my first PhD student, Jonathan Chardin, for example, something that we try to do, which is summarized here, is we try to do merger trees of bubbles, for example, like we do merger trees of halos, trying to see what is the merger rate of bubbles, what happens if I follow the most massive progenitor, therefore the largest progenitor in bubble vocabulary. And I try to you see, quantify the percolation process using merger trees, but we did something, we did few things, we obtained some results, but it was very hard and really not intuitive in order to extract information from this kind of representation of the percolation process. So something that we realized recently is that you see this field that I showed you previously, where you have at each pixel, here this is an example, the time where each region has been reionized, in fact contains all the information about the percolation process. Okay, and this is something that we've been doing later time. So again, the idea is that instead of considering, you see snapshots of the state of your universe in simulations at different times, okay, you only have one field that tells you at each pixel when it was reionized. Okay, therefore, you compressed a lot of information into a single quantity, the reionization time at each position, such as here. This is not new. This is something that has been done for a very long time in reionization studies, but it turns out that it has a lot to tell us, this field, something that we realized recently. The first thing is that, in fact, we can use it first to emulate reionization. I'm going to be very brief on that, but it turns out that asking, for example, a machine learning algorithm to be able to reproduce this time field, the reionization time field, for example, from the distribution of gas, distribution of sources, is fairly easy. Okay, which means that you can train, for example, neural networks in order to produce, you see, timelines of reionization. Okay, so of course, those neural networks have been trained on simulations, but they're able to produce timelines, you see, of the percolation of the bubbles as a function of time. And here you have an example of neural network prediction. Here you have an example from a simulation that took as so the model, the machine learning algorithm took as an input the same distribution of gas as the simulation, and it was able to paint, essentially, the bubbles as a function of time, but not by reproducing many different stages, but just by reproducing one single field that tells you when each pixel is reionized. And from there, you can reconstruct the full time evolution. So this is something that was done by Jonathan Chardin in 2019. More recently, something that we also realized is that you also can train machine learning algorithm to take as an input the radio signal, okay, from an instrument. So that, for example, a simulation of the radio signal of a given part of the universe. And this is the distribution, the real distribution of reionization times from the model, okay? And in fact, again, you can train a machine learning algorithm in order to predict what is the distribution of reionization times of a given radio map, okay? And that's interesting because you see, first, it shows you that reionization times is not a completely abstract concept. It means that at least conceptually, you can extract it from the radio signal. Information is here. But not only that, but it gives you, you see, the spatial distribution of when each places has been reionized. But something also to realize is that, for example, a radio observation is made at a given redshift. For example, here 11, okay? But this map tells you when each pixel will reionize, and it can even be in the future of a redshift of 11. Okay, it can be a redshift of 6, etc. Which means that you have, in a single slice, the time evolution of the patch of sky you're looking at. And something also that is interesting is here you have a time evolution, but in a transverse plane of the sky. Whereas the natural way to have time evolution is along the line of sight by scanning frequencies and scanning redshift. Here you have times, but in the transverse direction. And something that we're trying to explore right now is how can we check for consistencies between line of sight time evolution prediction from radio signal and transverse prediction of time evolution of reionization. And this is something that can be done with such kind of field. Okay. Very briefly, we try to do the same exercise with noise. Okay. It's worse. Okay, it's not, the performance are not as good as when we didn't have noise in the signal, but the large-scale structure of the reionization time map is still there. Okay, so at least there's some hope. Okay. And finally, because I don't have much time left, it turns out that something that we realized also recently is that the reionization time map can be studied using the same tools as people, especially here, have used to study the large-scale structures of the universe. So here, for example, you have an example of reionization time field that is extracted from one of our cosmological simulation of reionization. Okay, blue regions reionize at early time, red regions reionize at late time. Okay, and the thing we realized that, for example, if you spot what are the minima of this field, I mean places where the reionization time is the earliest, it corresponds to places where the first sources appeared. So if you're able to do statistics of the minima of the field, you are doing statistics of the first source that created light, essentially. The other thing that you can do is, for example, plot isocontours. Isocontours represent, in fact, if you think about it, bubbles. Okay. For example, if you take an isocontour of this field at a given time, it gives you the distribution of bubbles at this time. So if you're able to do statistics of isocontours, you're good to go. You know how the bubbles are distributed as a function of time. You can do, for example, gradient of the field. This is a map of the gradient of the field. Turns out that the gradient of reionization time is the front speed. Okay, is the propagation, is the speed of the signal propagation. Therefore, it tells you how fast radiation is propagating. If you're able to do the statistics of this field, you are able to do statistics of the propagation of radiation. And finally, here on the upper right panel, you have the skeleton of the field. It turns out that the skeleton is slightly more subtle to understand. It corresponds to ridges inside the field, okay? Which means that on both sides, you have reionization times that are at earlier time than on the ridge. And here, the location of the skeleton are all the places where the bubbles percolate, in fact. That's where they meet, okay? And you know, you have the distribution of when the different bubbles merged and where and when using the skeleton. So something that we realized with Emily Tilly, my former PhD student, is that there's a lot of information by using tools that were developed for, by Christophe especially, that were developed for large-scale structures in general, but applied to reionization time. And not only that, but something that we realized that those people, they developed a full machinery where, for example, if you assume that your field is a Gaussian random field, so therefore basically it's completely constrained by the power spectrum, you can make theoretical predictions about these quantities. So we could make, in principle, predictions on what is the distribution of places where bubbles percolate, distribution of places where radiation appeared, that kind of thing, using the same tools. And you see here on this panel, on the upper line, you see reionization time smoothed at different scale taken from a simulation. And here on the bottom line, here you see synthetic reionization time maps produced with power spectra, Gaussian random field, with the same power spectra of the simulation. Okay, so those are Gaussian random field on the bottom, and those are extracted from simulation. And it turns out that they are kind of similar, especially when you start to smooth on very large scale. You can, in fact, something that we realize is that the properties, and at least on very large scale, of the reionization time is very close to be a Gaussian random field. So this is something that we try to measure from a quantitative point of view. So here, for example, you have the distribution as a function of time. 0 corresponds to mean reionization time. This is the end of reionization. This is the beginning of reionization. So that's time here. And that's the distribution of minima value. Therefore, the distribution of times when radiation appeared. Okay, a different location. So something that you can see here is that simulation measurements are shown as crosses here. Okay, and prediction from Gaussian random field theory are shown here as lines, and the match is fairly good. Okay, so it means that in our models, which are at moderate resolution, okay, that they're not the best simulation we can do, it looks like, at least from the point of view of statistics of minima, like a Gaussian random field. Okay, so note, by the way, that the distribution of minima is skewed toward negative value, which means that the source, when they appear, they tend to appear before the mean reionization time, which is expected because that's where it starts. Here, for example, you have the isocontour length. Okay, so at first, you don't have any isofunction of time. Isocontour, at first, you don't have isocontours because you don't have bubbles. You have more and more and more bubbles, and then they start to percolate around the mean reionization time, and then they disappear because the universe is fully reionized. And this is something that can be measured by measuring isocontours and compared to Gaussian random field prediction, and it looks pretty good. Okay, it's not perfect, in fact, okay, because if you look at the theoretical line here shown in dark, if you look at the measures shown here as symbol, you can see that measured in simulation, for example, you lose isocontours much quickly than what you expect from theoretical prediction. And that's because, of course, the ionization process is not fully Gaussian. And what's happening is that ionization front, at the end of ionization, they accelerate. They go faster and faster and faster, and therefore percolation is more efficient than prediction from pure Gaussian random field. And here, those are prediction of skeletons, so I'm not going to discuss that, but the match is also very good. Not perfect, but still very good. Okay. Those are another discussion about non-Gaussianities. Okay, so I'm not going to discuss that. It's basically, I said what I wanted to say. Just to conclude, I'm going to show you what I'm doing right now. Okay, that's really what I'm doing on a day-to-day basis. The thing is that, so we are going to enter an era where you will have experiments such as SKA, okay, that will provide you, ideally, maps of the reionization, the gas being reionization at late time. Okay, no, during reionization, sorry. But the thing is that in terms of modelization, it's also super challenging. Okay, here, for example, on the right-hand side, you have an image, an actual image, right, obtained by the Nénuphar experiment, okay, which is a precursor for SKA-like experiment. The field of view, for example, of this experiment correspond at this redshift to volumes that are close to 2 gigaparsecs. Okay, so here, for example, you have a simulation that shows you the reionization times in a 2 gigaparsec box. Okay. Of course, you don't need to simulate 2 gigaparsecs, but as I showed previously, the state of the art currently, which are the CODA simulation, are able to model this kind of volume. Okay, so it shows you the difference that is between what you would like, ideally, and what we're able to do. So now we are trying to work, and the thing is that we basically did the max that we could do with this kind of tools that we have today. So now we need exascale supercomputers in order to be able to push our codes to their limits and try to do simulations that are consistent with what we are going to be observing. I'm going to spend a few minutes just to discuss the thing. That's 2 slides, okay? A lot of us, for a moment, are working and trying to use a new code, which is called Diablo. So Christophe said that it's a replacement for Ramses. I think that it's a little bit too early to say that, okay? But still, it's a route toward using AMR codes for cosmology in the exascale era. So exascale, so just so you know, is a word that just tells you about the next generation of supercomputers. And the next generation of supercomputers, that will be characterized by very high parallelization, okay, but also the presence of hybrid devices, graphics card, many different kind of processors and that kind of thing. Okay, so it turns out that our current codes, they're not really able to use this new kind of architecture. So that's why people are trying to work out new codes in order to do that. So for example, one solution to that could be Diablo. So Diablo is a code that is currently developed at the Commissariat Énergie Atomique. And in Strasbourg, we are putting a lot of time in order to try to do a cosmological version of the Diablo code. And the Diablo code is a super versatile code that is able to work on many, many different kinds of architectures. Okay. So that's what we've been doing. This is just a gallery of what we're currently doing. It turns out that we are able to do small simulations for a moment with Diablo, dark matter, gas, ionized bubbles. We're almost there. Okay, so that's what we're trying to do. And the code is super versatile because it's able to run on all this thing. So it's just another way to show you how, studying the reionization and how reionization time take place pushes us toward new methods and new codes. I'm going to stop here. Okay, so those are my conclusions. There's nothing new in there, and I just want to thank you for letting me present you my work. Thank you.
Questions?
With your simulation, will it be possible to estimate the number of black holes that are formed and the growth of these black holes and possibly the formation of supermassive black hole binaries at the epoch of reionization?
That's the kind of thing that are already made, let's say, in simulations that are not dedicated to reionization. Okay, it turns out that in our models, this kind of physics is not included yet. Okay, and but it's just a matter of time, plan, and that kind of thing. In principle, okay, you should be able to introduce this kind of thing and try to see, for example, what should be the impact of the distribution of X-ray emitters, which are related to the creation of supermassive black holes at every time, for example, on the radio signal and that kind of thing. But there's nothing that prevents us except time and manpower, so to say, to include the same recipes that are applied in standard simulation to our models. But that's not done yet.
Thank you for the very interesting talk. I have two questions. The first one is a clarification. When you were describing the inhomogeneity in the reionization, do you think that can be used as a way to constrain the applicability of the Copernicus principle? Because then the Copernicus principle. Because then at a certain scale, you have inhomogeneities, so you cannot apply that assumption anymore. But then maybe you can use this to say, okay, I have to go beyond those scales to say that my universe is actually homogeneous and isotropic.
Oh, yeah, for sure. That's the kind of, I'm not completely sure to see exactly what you want to say, but it's sure that, for example, using the reionization time field, something like we would like to see is, how far do you need to go in order to have something that is representative? And in fact, something that we haven't done yet is that people have been looking, for example, for the convergence in terms of neutral, you see the distribution of neutral bubbles. People have been looking for the convergence in terms of matter distribution for a very long time. And something that we haven't done is done it on the reionization time field. And maybe it's not the same scale, actually. I'm not even sure. Because as you see, the field is super smooth. And I don't.
And the second question is, do you consider magnetic fields in your simulation? No.
No, sorry, we don't. We don't. But it's not. It's an important question because, for example, you're releasing electrons, right? Okay, electrons that are moving around. And for example, there are a lot of people who are looking at reionization, for example, to see how do you generate the cosmic magnetic field, for example, that kind of thing. There are people in Orsay, for example, doing a lot of that. And that's definitely a relevant question, but we don't do that.
I was wondering when SK will be able to map the region. Will it be possible only from the H1 map, the redshifted, to have the large-scale structure? Because in your simulation, you can see the filaments and so on.
So this is something that I haven't done myself, but there's this paper, in fact, if I'm correct. Let me check. Those guys, Giri and collaborator, not this one, yes. Those guys, in fact, this is something that they try to do, again, using machine learning techniques. Okay, so you start from, I think it was the radio signal field, and they try to reproduce the large-scale structure distribution filament. I know that because, in fact, when we started doing this work, trying to reproduce ionization time, the first thing that we try to do is reproduce the the filaments, but it was already published. So people are already doing this. And it's true. I mean, you look at the bubbles, almost by eye, you're able to trace the large-scale structure. So
Okay.
the people are already trying to do that.
Thank you.
Okay. Okay.
In your map of the 21 centimeter fast method, you are comparing with the ground truth from the simulation, and there were very small bubbles at early times that seem to be not captured.
Yes,
by
that's an excellent point.
fast. Is that because it's flickering in the simulation and you don't capture this with the model? What's going on? No, the previous slide.
Yes.
There, the one on the bottom left.
Yep. So your point is that in this one?
Yeah, or the one on the bottom.
Yes.
You see very small bubbles
yes.
in the true simulation
yeah.
that are not there with the 21 centimeter.
Yes, fast. In the prediction. Yeah, it's because, in fact, what we've been using is convolutional neural networks. Essentially, you are filtering the field at different scales. And this is a generic feature of our implementation of convolutional neural networks is that we kill high frequencies. Okay, and therefore, that's something that we're working on, in fact, is trying to, to spot, to gain those small structures back. But this is something that you can see here, right? The original field is like this. This one is much smoother. You have the large-scale structures, no problem. But as soon as you try to look things that are the scale of a few pixels, you don't get them yet. But it's mostly up to our own implementation of convolutional networks.
Hello, thanks for the talk. So when you were talking about local reionization times with Milky Way and Andromeda analogs, so I understand that the simulations have been run with random initial conditions. I was just wondering if you've considered running these from constrained initial conditions of the local universe?
Yeah, that's a good point. In fact, this simulation is made from constrained initial conditions. Yeah, it's in fact, the CODA simulations also include people from the CLUES collaboration. And here this is this lead to a local distribution of galaxies that is similar to what is being observed. Yeah, that's the case.
Very quick question. What's the typical velocity of the expansion of these bubbles?
Oh, that's a very good point. So this is something that we measured, in fact, and at early times, so it's really slow. It's like 100, so maybe 0.1% the speed of light. But as fronts are able to propagate in the low density AGN, it can hit the very close to the speed of light, essentially, that we include. Yeah. So they're very fast. And in fact, that's, one way to reduce the cost of numerical simulation is actually to reduce the speed of light. Because when you reduce the speed of light, as long as the speed of light you see is much larger than the propagation, for example, ionization front, you're good to go. And that's true in many, many regimes. But at the end of reionization, where fronts are basically propagating in vacuum, right, almost vacuum, yeah, this kind of approximation can modify slightly what should be expected with a real speed of light. But yeah, at the end of the process, they are very, very quick.
Last question.
Yeah, so you showed that you can describe reionization, topology of reionization with Gaussian random fields.
Yeah.
But what are the implications of this? That we don't need simulations anymore, or?
No, that's a good point. First, something I want to say is that we haven't identified why for a moment, why it should be close to the Gaussian random field. But yeah, something, of course, that we imagine is that, I mean, generating a Gaussian random field, even a mildly non-Gaussian random field, is not difficult. So it means that, in principle, you should be able to produce a field that tells you when each pixel has been reionized from models of the power spectrum. So that's the kind of thing that you could imagine. Something also that you can imagine, for example, is that complement, standard cosmological simulation that assume, for example, very often an homogeneous redshift of reionization. Maybe you can populate this simulation, for example, with fields that would be produced, assuming a power spectrum and that kind of thing. And finally, one other implication is that something that we would like to do is to, of course, do physics. You're right. Relate, for example, the shape of the power spectrum to what is the typical, I don't know, time scale of when the sources appeared or what is their clustering and that kind of thing. And that's the kind of thing that we would like to work on. But yeah, the time is missing. Time is the topic of the day. That's what it is. But okay. Those are a few rules.
Okay, so Dominique will be here until 5 p.m. more or less if you want to talk to him, and let's thank him again for his presentation.
Thank you.